Here is a question. If you rotate a building mass and then move it, is that the same as moving it first and then rotating it? Try to picture it in your head. It seems like it should not matter. Either way, you have moved and rotated the same object. But it is completely different. And if you get the order wrong in Grasshopper, your geometry ends up in entirely the wrong place. Today, I'm going to show you exactly why and give you the rule that means you will never get this wrong again. I am Ajit Kumar. This is day 4 of 60-day Grasshopper course. We are covering scale, rotate and mirror and the most important geometry lesson of phase 1. Let's go. Quick recap. By the end of day 3, you could place a point, draw a line, draw a circle and move geometry using vectors. You understand the input-output model and you know how data flows left to right through definition. Today, we're gonna add 3 new transformation components: scale, rotate, and mirror. These are the components you will use in nearly every architectural definition you ever built. Let's start with scale.
I have a rectangle already placed in Rhino. Let me reference it in Grasshopper so we can transform it. Now, let's add a scale component. Double-click the canvas, type scale, place it. Let me zoom in so you can see the inputs clearly. The scale component has 3 inputs. G, geometry. This is what you are scaling. C, center. This is the point the scaling happens from. F, factor. This is how much you scale. Factor 2 means double the size. Factor 0.5 means half the size. Factor 1 means no change at all. Connect the curve parameter output to the G input of scale. Now, place a number slider for the factor. Double-click canvas, type number slider, set it to a range of 0.1 to 5.0. Default value 1. Connect it to the F input. Watch Rhino. Drag the slider up. The rectangle scales up. Drag it down below 1. The rectangle shrinks. Now here is a critical thing. Notice where the rectangle is scaling from. It is scaling from the origin, the world 0 point, because we have not connected anything to the C input. Grasshopper defaults the center to the origin. Watch what happens when I scale from the origin. The rectangle does not just get bigger. It always moves away from the origin as it grows. Every point on the rectangle gets pushed further from 0. That is scaling from the origin. Now let's compare it to scaling from the rectangle's own center. This gives you a completely different result. To scale from rectangle's center, I need to find the center point first. The easiest way is to use the area component. It gives us the centroid of any closed curve. Connect the same curve parameter to the area component's G input. Area component outputs two things, the area value and C, the centroid. That centroid is the exact center of our rectangle. Now, connect the area C output to the scale component C input. Watch Rhino again. Drag the scale slider. Now, the rectangle only gets bigger. It does not move. It stays center in exactly the same place because every point has been pushed away from its own center, not from the world origin. Remember this rule. Wherever your center point C is placed, that is the anchor. Everything scales away from that anchor. Origin center moves and scales. Own centroid scales in place.
Now, let's talk about rotate component. And before I show you how to use it, I need to explain something that surprises almost every beginner. Grasshopper does not use degrees to measure angles. It uses radians. You think in degrees, I think in degrees, everyone thinks in degrees. A right angle is 90 degree, a half turn is 180 degree, and a full circle is 360 degrees. That makes sense to us. But mathematically, angles are more elegantly measured in radians. In radians, a full circle is 2 pi, approximately 6.28. A half circle is pi, approximately 3.14. A quarter circle is pi divided by 2, approximately 1.57. You do not need to memorize any of this because Grasshopper has a component called degrees to radians. You type your angle in degrees, it converts for you instantly. Every time you rotate anything, that component goes in the chain, no exception.
Let's build the rotation chain. Start fresh to the right of our scale chain on the canvas. Place another curve parameter referring the same rectangle. Now, place the rotate component. Double-click canvas, type rotate, select and place it. The rotate component has 3 inputs. G, the geometry to rotate. A, the angle in radians. P, the plane that defines the rotation axis and center point. Connect the curve parameter to G input. Now, let's build the angle conversion. Double-click canvas, type number slider, set range 0 to 360. Label it rotation angle degrees, place it. Now, the conversion step. Double-click canvas, type radians, place it. Connect the slider output to the degree to the radians input. Then, connect the degrees to radians output to the rotate A input. Now, the rotation plane. Right-click the P input on the rotate component. Select Set One Plane. Click a point at the origin in Rhino, press enter. The rotation will happen around the z-axis through the origin, like a spinning top at the world center. Drag the rotation angle slider. The rectangle rotates smoothly, interactively. And because we use degrees to radians, the slider value is always in familiar degrees, but the rotate component receives exactly the correct radian value automatically. Now, for the most important lesson of day 4. Let's build two parallel chains to show the transformation order problem. Chain 1. Scale first, then rotate. Rectangle goes in. Scale factor 2. Rectangle doubles in size and moves away from origin. Then rotate 45 degrees. The already scaled and already offset rectangle rotates around the origin. Chain 2. Rotate first, then scale. Rectangle goes in. Rotate 45 degree first. Rectangle rotates around the origin. Then scale factor 2. The already rotated rectangle scales outward from the origin. They are in completely different places. Same rectangle, same scale factor, same rotation angle. Different order, different result. Here is the rule you need to remember. Every transformation uses their center point. The result of each step becomes the input of the next step. So, the position and the orientation of the geometry has when it enters each component determines where it ends up after the component runs. In chain 1, the rectangle has already pushed outward by the scale before the rotate ran. So the rotate spun a displayed rectangle around the origin. In chain 2, the rectangle was rotated around the origin first while still centered near it. Then scale pushed the rotated rectangle outward. Same operation, different order, different architecture. Always think about the order before you build a chain. The last transformation for today is mirror. Mirror reflects geometry across a plane, like holding a shape up to a mirror and seeing its reflection on the other side. Mirror has two inputs, G, the geometry to mirror, P, the mirror plane. The plane defines that the flat surface that the geometry reflects across. Let's mirror our rectangle across YZ plane, a vertical plane running along the Y axis. That means every point on the left side of the Y gets reflected to the right side. Connect the rectangle or the output of our scale chain to mirror's G input. The reflected copy appears on the opposite side. Move the original, the mirror updates automatically. That is a live parametric mirror. Any change to the source is instantly reflected.
Now, let's do today's exercise. This combines all three components.
Step 1. In Rhino, draw a rectangle 8 units wide and 4 units tall. Reference it in Grasshopper with a curve parameter. Step 2. Connect the rectangle to the scale component. Set factor to 1.5. Set center to the origin. Leave C input unconnected for now. Step 3. Connect the scale output to the rotate component. Slider 0 to 360 at 45 degrees. Degrees to radians in between. Plane at origin. Step 4. Connect the rotate output to a mirror component. Set a mirror plane to a YZ plane through the origin. Look at Rhino. You should have a original scaled and rotated rectangle and a mirrored copy reflected across the Y-axis. Two shapes perfectly symmetric. Drag the rotation slider. Both rectangle rotates in real time. Change the scale factor. Both get bigger or smaller together. That is a parametric symmetric composition.
That is day 4. You now know scale, rotate, degrees to radians, and mirror. And more importantly, you understood why orders of those transformations changes your result. Tomorrow, day 5, is the moment where Grasshopper stops feel like a complicated rhino and starts feel like a actual superpower. Because day 5 is about list. How to generate 100 pieces of geometry from a single component with a single connection. If this video helped you, hit subscribe. The full 60-day playlist is linked below. See you in the next one.